I want to know the name. So PB is equal to So PB is equal to P total into YB. So these are the two important equations and formulas I have taught from Raoult's law. Remember this thing? So the first equation, this is used when your solute and solvent is present in the solution. This is the formula which is used when they are present in the vapor form. Clear? Clear with these two equations? Now can you do the problems? What? Previous concept? 15 minutes. I thought today I'll be having a class in one school, but no class. If you want means I'll give it tomorrow. See, the solution it will take for more than 8 classes. In each and every day there is more amount of problem is there. I'll give you, don't worry. Or else this week you'll be having a physics test, right? About this next week is next week. So okay. So day after tomorrow there is no test. So this week for in 1 hour on the problem solve பண்றீங்களா? Okay, try to do this problem. Everyone can view this thing. See, vapor pressure of your chloroform and dichloromethane at 298 Kelvin, they have given their values. So which means vapor pressure கொடுத்துட்டாங்க. Okay, so vapor pressure in the sense that is nothing but your P0A and P0B. Both of them they have this things. Calculate the vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 gram of your dichloromethane. So first one is you have to calculate your vapor pressure of the solution. So what is the formula? Huh? Repeat. Oh, okay, okay. P total is correct, correct. So now calculate this thing. Hey, பண்ணுங்க. ரொம்ப நாளா மறந்துட்டீங்களா? So first one is P, if someone completed means just say the answer. Sorry, P total. P total is equal to P naught A XA. What? No, no, no. You don't need to convert. Keep it in this form itself. Don't convert. Okay. So here we have 200 mmHg. We don't know. Sorry, we don't know this XA. And P naught B is 415 mmHg and we don't know XB. Okay, so now we need to find this XA and XB. XA is equal to number of moles in solute by number of moles in solution, correct? Na plus Nb. So you have to find the number of moles. So first one is for your chloroform, CHCl3. So what is the number of moles of chloroform? Given mass divided by molar mass. Given mass is 25.5. Molar mass? Sure. One not? Wait. 12, carbon 12, hydrogen 1, chlorine 1, 35.5 into 3. Sure. I'll calculate only this thing. 12 plus 1, 35.3. 1 not 9.5. Everyone got 119.5. So 119.5. So what is the answer for this thing? 25.5. $25.5 divided by 119.9.5, which is 0.213. Got this answer? This is for chloroform. Everyone understood this thing? Feel this thing? Calculate for your CH2 dichloromethane. So for that thing, CH2 Cl2, given mass is 40, molar mass is 12 plus 2, sure, 85. 40 divided by 85. Zero 0.470. Okay, this is what the value we got. Now you can find your mole fraction of your component A and component B. So XA is equal to number of moles of solute A, that is 0.213 divided by 0.213 plus 0.470. Clear? So 0.213 plus 0.470. So which is 0.213 divided by 0.683. 0.213 divided by 0.683. So which means your answer is 0.311. So XA is 0.311 means XB is equal to 1 minus XA, right? So 1 minus XA, which is 1 minus 0.3. So which is 0.7. Got till this one? Understood the values? Huh? Okay, now substitute everything in your formula. P total is equal to C. You know the value of XA. XA is 0.3. Correct? And your XB is 0.7. So what will be your P total? 198. Sure. 200 into 0.3, which is 60, plus 415 into 0.7, which is 0.21. Wait. 200 into 0.3 and 400. Where 200? Where you got confused, man? What is your mole fraction value? 360. Correct. 350.5 mmHg. Okay. So now you solve for your first part. Correct. You have solved the P total. Second one, calculate the mole fraction of each component in vapor phase. Vapor phase means which formula you have to use? PA is equal to P total into YA. Okay, XA or YA. No issues. That is nothing but the mole fraction. So take that one now. PA is equal to P total YA. They have asked for mole fraction. So YA is equal to PA divided by P total. Okay. So what is our PA? PA is nothing but P naught A into XA. So what is the value of P naught A into XA? 200 into 0.3. That is 60. Divided by P total is, what is your P total value? 350. Correct. Okay. So 350.5. Can I understand? See, this PA is nothing but P naught A into XA PA. Correct. So P naught A is 200 mm and XA is 0.3. That is 3 divided by total is your 350.5. So just divide these two things. What's your answer? 60 divided by 350.5. So which is 0.17. Okay. So now this is your YA. So how we will calculate YB? YB is equal to 1 minus YA. Correct. So YB is equal to 1 minus 0.17. 0.83. That's it. When you're just adding or summing up 0.8 and 0.17, your value should be 1. Because always your mole fraction of the solute and mole fraction of the solvent, it should be always equal to 1. Clear? Yes. Got this one? Any confusions? See, do remember, vapor phase will always disclose vapor phase. Vapor phase is your formula. Okay. In solution, vapor phase of solution means P total is equal to PA plus PB. That is, PA is nothing but P naught A XA plus P naught B XA. Clear? Clear with this one? Now, புரிஞ்சதா? ஏதா doubt இருக்கா? Next problem பண்றீங்களா? Yes. Do this one. Very easy. Vapor pressure of solution. So P total is equal to, what will be your formula? Vapor pressure of the solution. P total is equal to, substitute and do it. So first one, let me see who's just saying this answer. right. 130. Huh? 130 mmHg. You can keep it here itself like mmHg because what we have discussed here, so don't need to convert anything. Okay, clear? Everyone got the answer? You want me to do it in the board? Everyone? Huh? Okay, so here P total is equal to P naught A XA plus P naught B XB. Okay, so here your P naught B is 100 mmHg XA plus P naught B is 150 mmHg XB. Now you don't know your XA and XB. XA mole fraction is equal to Na divided by Na plus Nb. That is number of moles of solute divided by number of moles of solute plus number of moles of solvent. So here they have openly disclosed 2 mole of component A, 3 mole of component B. So 2 divided by 2 plus 3, which is 2 by divided by 5 is equal to 0.4. So XA is equal to 0.4 means XB is equal to 1 minus 0.4, that is 0.6. So now substitute here. XA is 0.4 and XB is 0.6. So that is your answer. Okay, fine. This is 400 40 plus this one is 90 90. So totally your answer is 130 mmHg. Clear? Now you got Sandhya Namaste. Got this thing? So shall we try the third problem? Third problem is little bit complicated. Okay. Try this thing. So here, see, they have been asked, vapor pressure of pure benzene. So fine, we have to find the composition. Similar one. P total is equal to P naught A XA plus P naught B XB. Okay. So now, what is your P naught A? 957 mmHg into, we don't know our XA because that is what we need to find it. Correct? Composition. And P naught B one, the 379.5 mmHg into XB. So, how you will proceed after this? Okay, that's a given mass value. For that, you need the given mass value. So if they have given the given mass means we can go with the molar mass and we can do it. But here they have not discussed or disclosed the given mass. See here, this all reaction will be carried out in the laboratory where they will be using a standard atmospheric pressure. Clear? So when they are using the standard atmospheric pressure, which will be always equal to 1 atm. 1 atm is equal to 1 bar. In terms of Pascal, 1.01 into 10 to the power 5 Pascal, Pascal. In terms of mmHg, 760 mmHg. Clear? So now we can take this P total as 760 mmHg. Clear? This is nothing but in terms of pressure I have taken. Standard atmospheric pressure. It's a fixed value. Okay. So now 957 into, don't write this mmHg anyway, okay? Because it will be confusing. 379, finally you can disclose it, into XB. Now To carry this further, for XB, we can substitute as 1 minus XA. Do it in that way. So 957 into XA plus 379.5 into 1 minus XA. So 957 into XA plus 379.5 into 379.5 XA. So now do the calculations. Minus, sorry, minus. So what will be your answer? So 957 XA plus 379.5 minus 379.5 XA. So it means bring here this 379. 957 minus 379.5, which is 577.5 XA. Here 760 minus 379.5. So 760 minus 379.5. So which is 380.5, and keep your XA here divided by 577.5. So what's your answer? 380.5 divided by 577.5. So that is nothing but 0.65. So if your XA is 0.65 means XB is equal to 1 minus XA. Correct? So 1 minus 0.65, 0.35. That's it. So XB is 0.35 and XA is 0.65. This is actually fixed value. This is actually which is equal to 1 atmosphere, 1 bar. Yeah. So they won't do. All this kind of reactions happening in the standard atmospheric pressure. Clear? Everyone got this value XA and XB? XA is 0.65, XB is 0.35. Clear? Now fourth problem. Shall we move to fourth problem? Do this one. Vapor pressure of ethanol and methanol in 400 mmHg and 88 mmHg. So first one, you have to find the vapor pressure. P total is equal to P naught A into XA plus P naught B into XB, and second one in vapor phase. Okay, I won't do it. Make it fast and give the answer. They have given mass is 60 divided by molar mass. From that you can find the mole fraction. Okay. So with the mole fraction and the P naught value they have discussed. Okay. They have disclosed. From that you can find the P total. Chacha. Ethanol C2H5OH. What's the molar mass? 24, 46. Sure. 6, 12, 46. Next one, in number of moles. This is 40 divided by, for methanol, CH3OH. 12 plus 4 plus 12. It is 24 plus 4, 28. Twelve, 4, 16. Sorry, 16. So 32. 32. Sorry, 32. So what is Na? Point. I will get 60 divided by 46. 1.30. Okay. NB 40 divided by 32. 1.25. Okay. So now XA is equal to NA. That is 1.30 divided by 1.30 plus 1.25. So 1.30 divided by 1.55. 1.30 divided by 1.55. 2.55. So which means here your value will be 2.55. 0.509. So XA is equal to 0.509. So XB is equal to 1 minus 0.509. So which means 1 minus 0.509. 0.491. Got this answer? So now substitute P total. What is your P total value? Check it once more. Cross check it. 0.50. So 44 into, wait, I'll do it. 44 into XA is 0.50 plus 88 into, what is your XB? 0.49. So here your answer will be 44 into 0.50. 22. 88 into 0.49. 43.1. So it is like around 22 plus 43.1. 65. How you got 130? 100. Everyone got this value for P total? Okay, do the next. Huh? This is the value. P5. C is 0.5. X is 0.49. So I have substituted with the PA not PP not. So this one is P5. So now calculate the mole fraction of methanol as vapor state. You got 65. Okay, no issues. You can keep it as 66. No issues. Now calculate the mole fraction of methanol in its vapor phase. So vapor phase means what's the formula? Yeah. PA is equal to P total into YA. Okay. Do it. PA is equal to P total into YA. So mole fraction of methane. Where is the values? YA is equal to PA divided by P total. So what's our P total? 66. What is PA? PA is nothing but 44 into 0.50. So 22. 22. So that is 1 by 3. 3 dana. So which means 0.9. So that is your YA. 0.3. Sorry. Okay. So now your YB will be 0.7. They have not asked, but I'm just disclosing. Okay. 65.5. So you can round it. This is YA. No. This is PB, methanol. YB. Okay. Ethanol, methanol. I can't. Okay. Wait. Hey, no. So PB is equal to 88 into wait. 88 into 0.491. So which means PB is 1.43.2. So 43.2 divided by 66. 43.2 divided by 66. 0.65. Who said 0.3? Huh? 1.3. So here if it is 0.65, which is your YB, Apo 0.35 will be your YA. That's it. What is P? PB. PB is nothing but your P naught D into XB. P naught D and 88. XB what you calculated? 0.491. So 88 into 0.491. That is nothing but 0.88 into 0.491. 43.208. Okay. You got this one. Everyone got this one. Okay. So here we can stop the problem part. Now we can enter into the next concept. So do remember in Raoult's law, there is two important formula. So before Raoult's law, you have seen another one more thing, that is Henry's law. What is the formula used for the Henry's law? P is equal to partial pressure is equal to KH into X. Okay, so here in Raoult's law, you're using two important formulas. First one is the vapor pressure of the solution. Second one is using vapor phase. Clear? So these are all the possible problems that will be asking you at some point. Clear with this one? So now we are moving to our next part, that is ideal and non-ideal solutions. See here itself, here are. Second part, mole fraction of the methanol in vapor phase, that is 0.65 YB. Clear? So your YA will be 0.35. So shall we move to the next one now? Ideal and non-ideal solutions. Okay. So first one, don't see this. Keep your mind. You are making a solution. Okay. So you are just taking your solute. So in the solute, all your solute particles will be having a kind of intermolecular force of attraction. Okay. Let it be in this case. So this is your solute. Okay. So in solute, so let's suppose A is your solute particle. Okay. So it will be attached with another similar solute particle A. So likewise, B is your solvent. It is attached with another solvent B. So now when you are making the solution, definitely there will be a force between particles, correct? Intermolecular force of attraction. So this intermolecular force of attraction can be of anything like dipole or dipole-induced dipole, van der Waals or London force or hydrogen bonding of anything. So when this solute and this solvent are combined together, what we are just forming? Solution is forming. So which means A and B. So here the bond or the attraction formed between a new one. Correct? So here what happens when you are forming the solution? They break the bond. Correct? So in solute, all the particles will break the bond, and what happens in the solution? The solute and solvent combine together and they form a new bond. This is the practical thing. What happens when you're mixing your solute and solvent? Clear with this thing? Okay. Huh? Okay. So clear with this part, the solute and solvent. Okay. So now Coming to the ideal solution. Okay. What happened? That's okay. After the class over, you can take it. So now, in ideal solution, how much amount of number of solute particles you are taking? How much amount of solvent particles you are taking? That much amount of equal amount of your solute will be combined with the solvent and it forms a perfect ideal solution. Okay, clear with this one? Huh? See, ideal solution. How much interaction there between the solute and the solvent particles? Okay, the solute is there. Okay, there is more solute particles. It will not. Okay, everything will be combined with the intermolecular force of this solvent. Everything will combine with the intermolecular force. We have to find a solution. So, how much amount of intermolecular force attacks there between the solute and solvent? That much amount will be there in between this. Your intermolecular attraction between solute, 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 solvent, solvent, solvent. When you are preparing the solution, solute, solvent, solute, solvent, then we have a force of attraction, right? So that force is also equal to the solute and solvent. Which means before mixing, what is the kind of attraction is there? After mixing, also similar kind of physical attraction. This is the ideal solution. I question this. In reality, is it possible? Nothing is 100% ideal. Okay, no solution can attain 100% ideal solution. Even as a student, even as a tutor, for you also can't do 100. You can't also be 100% perfect, and I cannot be 100% perfect. So at least we will try to be perfect, right? Try pannuvolyo. So that is known as almost it will near the ideal solution. Okay, almost it will try to act as the ideal solution. So if they are trying to act as the ideal solutions, what are the conditions should be there? First, they always take Raoult's law at every concentration. So what is Raoult's law? P total is equal to P naught A into XA plus P naught B into XC. This is what your Raoult's law. So which means at every concentration in the sense, remember the graph. What is the graph that I have drawn on that day? Left side, right side. So in between, I have said there is a concentration part will be there. What will be on the leftmost side and rightmost side? How I have denoted the XA and XB. Which means 1, 0 means it is present as a pure solvent. 0, 1 means here it is present as a pure solute. It is that form. In between this 1 and 0, you can see many amount of concentrations will be present. So that amount of concentrations is nothing but at each and every concentration, you can take your PA value, your PB value, and your P total value. Do you remember the graph? You want me to draw the graph? Huh? PA, that is PA, that is P total, PA plus PB, correct? So at each and every concentration, you can take your PA, PB, and P total value. So at each and every concentration, this ideal solution will obey the Raoult's law. Clear with this one? You want me to draw the graph and explain? You know about the graph, right? Yes. Second one is delta mixing enthalpy. What is delta mixing enthalpy in the sense? If I'm taking a sodium chloride and I'm dropping it in water. So what happens? I will use to keep on stirring. Why do I keep on stirring? To mix it up. Uniform distribution. What happens? I should break the NH bond. So what happens? It will combine with the H2O. H2O will combine. So which means I'm providing the energy to break the bond. Correct? So for breaking the bond, I'm providing the energy. And for the formation of the bond, what happens? The energy will be getting released. Clear? So this delta mixing will also be always equal to 0 in the sense. Let's suppose if I am taking solute of AA, okay, and solvent of BB, it is forming a solution of A and B. So here, to break this bond, I am applying 10 kilojoule mole energy. And here, to break the bond between the solvent particles, and I am applying 10 kilojoules per mole. Okay, in solution, Okay, it will be like what happening in the sense there will be formation of new bond will be there. So formation of new bond in the sense the energy is released. Clear with this one, the energy is getting released. So here what happens, it will be 20 kilojoule per mole. So which means calculate the net charge. Okay. Exactly, zero. So which means your delta mixing enthalpy should be always zero in the sense. What is the thing? The amount of energy that is provided to break the bond will be always equal to the amount of energy that is released during the formation of the bond. Clear? And next one, last one is delta mixing volume. What is delta mixing volume? Okay, if I'm taking 10 ml of solute and I'm taking 10 ml of solvent, if I'm intermixing, it should be exactly 20 ml of my solution. That is nothing but your equal mixing of volume, correct? You have to mix. So which means in solvent, there will be some kind of interaction, intermolecular force of attraction will be there. In solute, there will be some sort of intermolecular attraction will be there, correct? So when I'm mixing all the two things, what happens in the sense? What amount of intermolecular force of attraction is there between the solute and solvent, that should be equal in the solute and solvent. Clear? So in a test tube, if your solute, if this is 10 ml and this is 10 ml means exactly 20 ml of solution should be obtained. That is your delta mixing volume. No change in enthalpy. But in reality, is this possible? Ingle yoshi paranga. You are taking two test tubes. 10 ml of I'll give a break in 10 minutes, okay? 10 ml of your water and 10 ml of your some alcohol. You're intermixing, okay? In another one more liquor. Exactly 20 ml will be there. There will be some point difference will be left over, right? So nothing is ideal solution, right, in this world. Okay, but they will try to be 19.7 ml will be there. 19.7 ml will be there. That remaining 0.3 in the sense which is an imperfection, correct? So nothing is the ideal solution. But if it is ideal solution, then it will be all these types of conditions. But it is not practically possible. So now you are getting the non-ideal solution. Clear with this ideal solution? Any doubt? What are the three conditions you got this thing? Okay, now while we are not talking about the non-volatile. Okay, so you know you have seen about that. Now these are the three important conditions. So nothing is like that, but nearing almost 99.9%, 99.5% ideal solutions will be there. So for that, I have disclosed some examples. These are all the examples of the ideal solution. See, if you are mixing this heptane and hexane, the solute and solvent, they'll be having equal amount of intermolecular force of attraction. Their characteristic will be remaining same. Correct? But there will be a minute amount of difference will be there. Correct? So these all are examples of your ideal solutions. Nearly ideal. So they will be saying as I am only ideal. Nothing can be ideal in this world. This is your textbook. Xylene. IUPAC name of xylene. Wait, I took forgot. Wait, I do want. I forgot. I'll say. Xylene is there in your organic organic chemistry or studying xylene structure. It will be come under. Sol. Yes, yes, yes. So this is toluene. Another CH3 will be there. This is xylene. Do you know about cresol? We studied this in any of our alcoholic speaker and halogene and halogene. Studied. Clear with this one? Next one is non-ideal solutions. In a joke. No, nothing. Okay. Next one is non-ideal solutions. So in non-ideal solutions, ideal solutions, they obey Raoult's law. Non-ideal solutions, they do not obey Raoult's law. So which means in Raoult's law, definitely we will be seeing a deviation. Correct? So you can see the deviation will be of this time. PA, PB, will be coming like this. Correct? Okay. So if this non-ideal solution is not obeying Raoult's law in the sense, it will be showing the deviation like this and this. Correct? So there will be a deviation. So first one is delta mixing enthalpy will not equal to 0. How it is not equal to 0? How there will be a change in enthalpy? They releasing a form of okay. Like cracking sound, charring sound will be there. Okay. So here, see, no change in volume and no change in enthalpy. Two cases are there. So change in enthalpy. Change in enthalpy. So here it will be. Both del H and del B both will be changed in enthalpy and change in volume because there in ideal solutions everything will be equal. Okay, whatever you are just taking your solute and solvent, both of them will be equal to the solution. It's clear, but here they will not at all obeying Raoult's law in the sense which no, both of the things will be not equal to 0. And what happens in their volume and also in terms of energy, there will be change will be there. It will be happen in terms of two conditions. See, I said if this is your line in the sense, two deviations will be coming in both the sides. So one will be positive deviation and another will be negative deviation. Clear with this one? So here, this non-ideal solution is showing the positive deviation. So if it is obeying Raoult's law in the sense, the line will be straight. When it is not obeying in the sense, what happens? Two kinds of deviations will be there. One will be showing the positive deviation and another one will be showing a negative deviation. Clear? So here, when it is showing the positive deviation in the sense, at that time, this is your solute particles and your solvent okay, and written in this way. So now you can read the statement and you can understand it. Inside positive deviation, the solute particles, the force of attraction, that is the intermolecular force of attraction, will be high. So here, in solvent particles, the intermolecular force of attraction is quite high. Okay. In terms of solute solvent particles, here the intermolecular force of attraction is quite low, which means the intermolecular force of attraction is low in the sense there will be more amount of repulsion you can see here. Okay. So if you're seeing more amount of repulsion here in the sense, you can understand this one in positive deviation. Okay. See, your solute and solvent, if both are facing more amount of repulsion in the sense, whether it can easily form vapors or not. No. No. How formation of vapors, how it is easy? Like when the formation of vapors is easy? Less. So here there is weak intermolecular force of attraction is there. No? So now, here what happens? The formation of vapor will be more clear. So in this condition, in the positive deviation, here in solute particles, the intermolecular force of attraction is high. In solvent particles, the intermolecular force of attraction is high. But here it is quite low in the sense there is the intermolecular force of attraction is less and there is more repulsion. If there is more repulsion in the sense, the particles will try to escape as a vapor. So which means more vapor will be there. So here you can see more vapor. So once more vapors is present in the sense, it will exert more pressure. So more vapor pressure you can see here. Okay. For this thing with positive deviation, always your solute and solvent particles will be having a low intermolecular force of attraction compared to solute and solvent particles. Clear with this one? Yes. So coming to the next one. Okay. So here, can you compare the Raoult's law with this Raoult's law of ideal solution with this non-ideal solution? So there we have seen solute particles is equal to solute solvent particles. Clear? So which is equal in terms of ideal solutions and Raoult's law. In positive deviation, you can see this will be having a low intermolecular attraction. Here it will be having a high intermolecular attraction. In negative deviation, it will be quite vice versa. So now we can see this delta mixing volume. It is positive. Can you say how it is positive? As I already disclosed, it's a positive deviation. So how it shows the positive deviation? Huh? Exactly. So if your solute and solvent, when they're combining together, what happens here in the sense you're taking your solute, okay, so this is your solvent. When they are present as a solution, see here, already I disclosed here, there is only low intermolecular force of attraction, correct? In between your solute and solvent, when there is low intermolecular force of attraction means there will be more repulsion will be there. So all your solute and solvent molecule will try to move far away from each other, correct? So it will move far away from each other in the sense what happens, your volume will be getting increased, correct? So once your volume will be getting increased in the sense, definitely it shows a positive deviation, higher value. See, this is 10 ml, this is 10 ml, correct? So if this solute particle is not properly having a force of attraction with the solvent particle, means what happened? They will be moving far away. So which means here you can obtain 22 ml. Clear? Because of the repulsion. Purida. The total amount will be getting increased. Okay, because see, when it is tightly packed in the sense, you will be getting, it is very close in the sense, what happens? Your volume will be getting reduced. Okay, so as we said, ideal solution 20, 10, 10, 20, that is not obtained. Okay, ideal solution means 10, 10, 20. If particles are very much close in the sense, what happens? It will be getting decreased. If the particles are very much far in the sense, there will be increase will be there. So exactly 2 or 1 ml will not be seen. Definitely you can see at least a 0.1 or 0.2 difference. Clear? So this is because of the low intermolecular attraction and high repulsion between your solute and solvent particles in the positive deviation. Clear with this one? So here, this is why your delta mix volume is positive. So that is why you can see 10 and 10. You are taking 10 ml of solute and 10 ml of solvent in the sense. You are not obtaining 20 ml. More volume just you are obtaining than the expected, than the observed. Clear? Clear with this one because of the repulsion. And now, can you say how this delta mix enthalpy is positive endothermic in nature? Absorbs energy to. Okay. So here, what happens in the sense? See, you're taking your solute and your solvent. Clear? So if you are giving 10 kilojoule mole to break the solute particles, again 10 kilojoule per mole to break the solvent particles. Okay, but here in this positive deviation of the non-ideal solutions, you can see there is only less intermolecular force of attraction is there. Okay, so which means maximum repulsion is there. So your formed solution bond is very, very weak. There is only less kind of attraction is there, more repulsion is there. So your formed bond is very, very deep. So which means here if it is 10, here if it is 20 in the sense, say for example, you can say minus 15 kilojoule per mole. You can say like minus 5 itself is enough, 5. So minus 5 kilojoule per mole. This itself is enough for the formation of the bond. So which means it is releasing only a less amount of energy. So now calculate the net charge 20 minus 5, which is nothing but your 50 kilojoule per mole, which is positive. So here you can see your endothermic reaction nature. Here with this one, the bond is solution minus product minus reactant. Okay, minus 5 plus 20 plus 20, 10 plus 10, 20. Minus 5 minus 20. Endothermic is positive in nature. Exothermic is negative in nature. So minus 5 plus 20, which means what happens? Your plus 20 will be there, right? So I have written 15. Correct, Anna? Minus 5 plus 20. Whatever you're taking, endothermic, okay, when endothermic reactions happen, you're giving the energy for that molecule to break the bond, which is positive in nature. Yes. Okay, so it is negative. Yeah, change in enthalpy. You're saying about the del H enthalpy value, del P minus del R, அந்த மாதிரி பாக்குறீங்களா? You're saying only that thing, right? Delta H enthalpy. Why you want to see that thing? Net charge only we need to calculate, right? We are only seeing how this delta H mixing is just happening, right? Change in energy. Why are you going to the formula? If you are going to the formula in the sense that some cases it will be del P minus del R, some cases it will be del R minus del P. Okay, so just take this one. When your energy is getting released, anything is wrong today? Nothing is wrong. So here when energy is released, it will be minus inside, it will be plus inside. Okay, don't go to the formula. If you are just going to the formula, you in chemical bond only you will be taking that formula for the proper chemical equation. Here just the net charge is enough. Okay, plus 20 minus 5. So it will be endothermic plus sign will be this. No, in some cases it will be product minus reactants also there. Bond energy, bond enthalpy in chemical bond you have studied. No, sometimes you'll be taking reactant minus product, product minus reactants also some cases. So that's where you are taking the net energy. Yeah, because here it's strong, no, the bond is strong. So we are taking the reactant. 20 minus 5. 20 plus 5. Wait. Okay. So you're saying 20 minus 5. That is delta, reactant minus delta product. Is it the only formula you have studied? I'm asking the question. Is that the only formula you have studied? Chemical bond. Chemical bond. Have you studied about chemical bonds chapter, right? Thermodynamics. In chemical bonding only you studied about this thing, right? Thermodynamics. Chemical bonding, hybridization, your valence bond theory, you will be studying in there now, chemical bonding. Okay, so thermodynamics. Oh, according to thermodynamics, you are saying this thing. So in thermodynamics, it will be. Okay, so in thermodynamics, it is product minus reactants, del H, delta enthalpy. So there you are saying the Gibbs free energy, all that kind of things. Okay. So you are calculating according to that thing. Okay, fine. You just take it in that way. But wait. Thermodynamic, both things, endothermic or exothermic, whatever. Okay. So there, amount of energy supplied, amount of energy released. Right? That is for the constant thing. So you are using the formula there. What is the formula? Enthalpy of product minus for your change in enthalpy. But in this non-ideal solution, we have not taken that formula. Only calculate the net energy charge. You can see in your net energy. Okay, you take the product minus reactant also. But you know, Singe's publications book. You have seen that book, Singe's publications books. There is no difference. If you want, you can take in this calculation also. No issues. Net energy charge means delta product minus delta reactant. You can take in that way. Okay, clear. Anyways, it's a positive value. Endothermic in nature. Clear. How it's negative? Minus 5 minus minus 5 minus 20. Oh, minus 5 plus minus 20. You are saying in this way. Delta, 1 minute, just wait. So the product minus reactant. So minus 5. Okay, I'll check this one and I'll let you know tomorrow. Okay, I'm just got confused with this one. See, wait a minute. if you are just applying this formula, the value will be negative. So it will be exothermic in nature will be there. Correct? So, but for positive deviation, it is endothermic in nature only. Okay, okay, I'll let you know with this reaction. I'll check the book and I'll see. Okay, somewhere I have committed the error or not. Okay, fine. So just leave this one. See, that depends upon the solute and solvent you are taking. So here we have taken more of, see here, we have seen many examples. Okay, so the solute will be arranged in one type. So what happens? The kind of interaction will be strong. In MK, the kind of interaction will be strong. So when you're taking this different solute and solvent, when you're mixing together, we can't say both will be having the same ability to combine. Correct. Depends upon the solute and solvent. Okay, so it can be high, it can be low. That is why here these are all your examples. Okay, so which means you are taking your solute and your solvent. You are just combining both the things. Okay, so which means one is not combining with the other one. Either your solute or either your solvent is not properly combining with your solute or solvent. So that's why what happens when intermolecular attraction is getting weak and the repulsion is getting higher and it is just getting far away from each other. Clear with this one? Yes. I'll check on this one. I'll let you know. But this is endothermic in nature. I'll check with this one. I'll let you know. Okay. Already I'm in a confused state. Break. Wait. Oh, எதுல போட்டு இதெல்லாம் நல்லா சொல்லுங்க. I don't want to think and all. Okay, now we can plot this graph of the positive deviation. So first one, according to Raoult's law, we can draw the graph. XA is equal to 1, XB is equal to 0. So here XA is equal to 0, XB is equal to 1. So here it's pure solute. So P naught A, pure solvent P naught B. So is equal to 0.8, 0.6, 0.4, 0.2. P is equal to 0.2, 0.4, 0.6, 0.8. Okay. So here P naught will be PA is getting decreased. It's getting decreased. Clear? So in positive deviation, okay, so as we already discussed, the intermolecular force of attraction is less. Due to more repulsion, what happens? The volume is getting higher. Clear? So what happens? The expected value will be more. Okay, actual value, whatever the actual value we got, it will be more than the expected value. So the graph will be plotted in this way. Okay, for positive deviation, this is P total. P total is equal to P naught, PA plus PB. This is enough. Okay, so this is P real, which is equal to PA plus PB. So here, this is for PB. Again, it will be quite higher. Again, for PA, it will be quite higher. So here, at this concentration, okay. So here, according to your Raoult's law, what happens? Your PB value is this thing. Okay, but according to the reality, non-ideal solution, positive deviation, the PB real value will be this thing. Okay, so now here you can see, according to the Raoult's law, the PA value will be PB. PA value will be this thing. But according to the positive deviation, it will be P real, that is PA. And here P total according to Raoult's law, and here will be our P real, that is PA plus P. Here with this one, because why this kind of excess value is shown this is because the solute and solvent particle is facing more amount of intermolecular repulsion. Okay, so that's why you can see observed value will be higher than the real value. Okay. Positive deviation. Okay, so similar one is applied for the negative deviation, but in negative deviation, everything will be in the upside down way. Okay, so now these are all your examples of acetone, ethanol, water, ethanol, carbon disulfide. Okay, copy this one. Shall we move to next one? Okay. So in negative,
can you show the graph one more?
It is like solute particles, okay, and your solvent particles. So here you can see this solute and solvent particles will be having more intermolecular force of attraction between each other. Clear with this one? Why we are having a more intermolecular force? Huh? Less repulsion. Huh? You see here, your solute and solute, your solvent and solvent, everything is having an intermolecular force of attraction. Okay, I'm not saying this is strong. Of course, it is having intermolecular force of attraction. But when you're just producing a solution, there your solute and solvent combining together, they'll be having a very much amount of strong intermolecular force of attraction. There, what we see, it's a weak intermolecular force of attraction. Because of the weak intermolecular force of attraction, what about its vapors? Easily it is getting forming vapors. More number of vapors you got to know form, and more vapor pressure is getting exerted. Clear? So here, what about the vapors formed here? Less amount of vapors. Less vapors will be formed here, and less vapor pressure will be existed here. Clear? Because solute and solvent are tightly packed with a strong intermolecular force of attraction. So easily it won't allow to convert it into vapor form because it is held by a strong force of attraction. Clear? So now see this one again. I'll check this part and let you move this exothermic part. Okay. Even I got confusion. Coming to the volume of the solution. There you can see more volume of solution is observed. But here, less volume of solution is observed. Why less volume of solution is observed? Because more amount of interaction is there. So more amount of interaction is there in the sense all your solute and solvent molecules will be tightly held with one another. So which means what happens? The volume will be getting reduced. So 10 ml of solute and 10 ml of solvent you're taking in the sense it will be 19 ml of your solution will be produced. Okay, there'll be 0.0, 0.7, 0.6, 0.5, that kind of very minute amount of differences will be there. Clear with this one? So here less volume of solutions observed than expected. That is for your negative deviation for the non-ideal solutions in Raoult's law. Clear? So how can you draw the graph for this one? There you have drawn like this. So here you have to draw it like this. I'll be drawing any two values. I'll be writing any two values. So here it will be P naught A, P naught B, formula of enthalpy of change is delta product minus delta reactant. So here less volume is noted, right? So your graph will be in this type. Correct? So all your curves will be below the Raoult's law graph. Okay, so here you can see if this is your expected, okay, PB na. So in negative deviation, your PB will be here. Okay, and here you can see if this is your expected PA according to your Raoult's law means here you can see your PA real according to the negative deviation. So this is your P total according to Raoult's law means according to negative deviations you can find value here. Here in two kinds of we have discussed the two things, that is positive and negative deviations. Just look through the graph and everything. Here. So now these are all the examples of the negative deviations. So after completing this, solve some problems. Try this problem. Anyacha. So here, initially they have asked the vapor pressure of the solution to two pure liquid, PA0 and PB0 they have disclosed. When they form the solution of total vapor pressure of the solution 600 mm. P total also they have disclosed. So P total is equal to PA0 XA plus PB0 XB. P total is 600 mm. PA0 is 450 mm XA plus PB0 is 750 mm XB. So you can substitute XB is equal to 1 minus XA so that you can, it will be easy for your 1 minus XA. Which one? So exactly, you have got 0.3. Next, calculate the second part. Composition in paper case. Six hundred minus 200 minus 7, which is 200 minus 7. No, 300 minus 7, 600. Divided by 300 is what is the vapor phase answer? V is equal to P total into YA. So YA is equal to PA divided by so PA is this one 450. PA is 450 into 0.5. 450 into 0.5 on the 225 divided by P total 600. So 225 divided by 600 is 0.375. So PB is equal to 1 minus 0.375 is like 0.7. 0.625. P 0.625 is your P. Got the answer? Everyone got the answer? Finished? XA, XB 0.5 you obtained. PA, PB, got that. Huh? 0.375. Are you off?